So this one is the logarithmic functions, right? And their graphs. A little less emphasis on the graphs, just like in the first section, there's a little less emphasis on the graphs than exponentials. So definition of a logarithm, right? This was the box. I think if you copied the things I did, I signed as extra credit, you have already had these. So they say log base A. A logarithm has a base, right? It's usually after the log for logarithm, it's a number which is written as a subscript, right? That's the base of the logarithm. And so you can see that if you have y equals log base A of x, that means that there was an exponential which was x equals a to the y. Those are saying the same thing. It's the same relationship, just kind of written in two different ways. So notice the conversions here. Right? The base of the logarithm is the base of the exponential. The exponent of the exponential, that's what the logarithm equals. That's not good. Which means logarithms are exponents. Okay, that's what they are. So, I mean, you might have done some of this in Algebra 2, where you go from like one form to the other, like here's the exponential form, here's the logarithmic form of the same thing. They actually took that out of the SOL this year, so they're not going to be equal. To me, it's like hard to talk about exponentials without talking about logarithms, and the things that tie them together are that they're inverses of each other. And the way you know that is because you make this conversion, which we'll do in a few slides. So if 3 squared equals 9, that means log base 3 of 9 equals 2. Right? So the base of the exponential is the base of the logarithm. The exponent is what the logarithm equals, and the 9 is the argument. When you go back and forth between them, for me, the way that I always think of it is like this. I always start with the logarithm. 3 squared equals 9. 5 to the third is 1.5. I mean, it's visual, for me, this statement. 5 to the third equals 125, so log base 5 of 125 equals 30. Basically, it's saying, what exponent would you raise the base to get the thing that's inside the logarithm? So logarithms were invented around 1610 by a guy named John Napier. When I was in college the first time at Kansas State University, there was a time when, I think I was in a math education major for a while, and they had me take this class called the History of Math, and I had to do a report on anybody, and I ended up doing him. I don't know why I did him. I mean, I had no particular interest in logarithms. It might have been just like the lesser of, bad choices or whatever. But I remember doing it on this guy, John Napier, which, by the way, we used to have a student here by that name, John Napier. He had a little sister, Jenna Napier. I don't know if anybody here knows the Napiers.
Swim coach.
This is
Swim coach.
Jenna?
Yeah.
Okay. Yeah, I think she was probably a swimmer. So her brother, older brother, had that same name, John Napier. I remember from the report that I gave a couple stories of this guy. This is like, again, in early 1600s. He was some rich British guy, or maybe a Scot, I forget. But so we had a bunch of servants, and he thought the servants were stealing from him. So in order to catch the person that was stealing from them, understanding they were all kind of superstitious and all this stuff, he had them all like go into a dark room one at a time, and suppose there's this rooster sitting on the table, or a hen or something, and they were supposed to pet this thing and then come out on the other side. And so they did, one by one, they go through there. Well, the rooster had this like coal or something black all over its back. So when they pet it, they got their hands all dirty. Except for the one guy who was guilty and was afraid that it would be found out if he petted this rooster. So he came out with a clean hand. So that was a John Napier anecdote. The other is he was angry at his neighbors whose pigeons kept coming all over his yard, leaving their messes. So he put out a bunch of peas soaked in alcohol, and then they got all these peas, got drunk. He went over and picked them up, threw them in the bag. Those are my memories of John Napier. So the thing about logarithms is by converting numbers to their logarithms of a common base, you actually are able to replace multiplication with addition, right? We know that when you multiply two numbers of the same base, you add their exponents. So instead of having to multiply two huge numbers, I can just add their exponents. That was a big simplification in days before computers and calculators and all that, to be able to do that. So, that's what they were first used for. So I had a couple anecdotes here. So, in fact, we use this. I graduated high school in 1976, and the first calculators you could get in those days were about 1975 or so, and they were Texas Instruments. It was SR10, and they were huge, and they did four things: add, subtract, multiply, and divide. That's it, right? Before that, we had to use slide rules, right? And a slide rule, this is what we were taught to do in class. Just in an Algebra 2 class, you'd be using a slide rule to do some of the more complex calculations. And with a slide rule, what it does, it has a logarithmic scale of numbers here, and then the logarithms themselves are on the top of it, although you don't actually even use those. And it has a sliding bar that goes through the middle of that. But for example, if I wanted to multiply, this is an easy example, but if I wanted to multiply 7 times 6, right, I would slide this right side of the scale, it's a 1, over to the 7, and you have this thing, it's got a really fine line on top of it. You would make sure that it lines up really exact, right? And then you would, now that that's lined up, I would go over to the 6 and read down on that scale, and it's in between the 4 and the 5, it's 42. It's actually like 4.2. But you would have to know, well, 7 times 6, that's going to be more like 42. So that's how we used to do calculations before calculators, using a slide rule. This was my dad's. He was an engineer. This was his slide rule. So, anyways, so I Googled it just to make sure my memory of this was roughly correct. Like up until the 70s that engineers used this. They said until 1972. That was the first time that Hewlett-Packard came out with a calculator that you could do calculations with. And he probably had it, because he was a professional. But as far as kids having it in school, like I say, that might have come along a few years later. Okay, so that's one thing about logarithms. Second one. So you can see this is what we mean by a logarithmic scale. Notice how this is what we call in meteorology skew T log P diagram. The skew T is because these are temperature lines here in Celsius, 0, 10, 20, 30. But notice they're not going like straight up and down. They're skewed. They're going off at an angle like that. The log P is logarithm of pressure. So the pressure is, that we use to measure the pressure in weather, its surface pressure is in millibars. That's 1,000 millibars right there. There's 900, 800, 700, 600. But notice how the spacing increases as you go up. That's a logarithmic scale. Okay, now it's important for this diagram. The reason that they do that is because of an equation, what we call thermodynamic energy equation. You're able to look at one of these here. This is the temperature as somebody sent a balloon up into the atmosphere. As the balloon kept rising up in the atmosphere, it was radioing down the temperature, pressure, winds, all that kind of stuff, humidity, All that stuff was being sent to the ground. This was the trace of the temperature. You could see at the ground it was close to 20, let's say 19, I think that's around 66 Fahrenheit. And it actually increased, that's an inversion near the surface, which is kind of common overnight that you get an inversion. And then it starts to decrease, right? And so this is the trace as you go all the way up. You know, you're up 200 millibars, that's like 40,000 feet or so. It depends on the atmospheric conditions exactly where it would be. But this is the thing you look at when you're forecasting thunderstorms. I mean, you want what's going to happen in a thunderstorm is that some little bit of air that's down here, which has its own temperature and humidity, is somehow going to be forced to go up. And when it gets to the point, like here, where it's actually less dense than its environment, it's buoyant. It's going to keep rising. So once it gets past this temperature line right there, all that, nothing's going to stop that thing from going up very quickly. That's upward vertical motion. That's what ultimately causes the thunderstorms that we get. Because of the scale being a logarithmic scale, all this area here can be converted into energy. So you can look at this and kind of assess like how much energy is going to be in this thunderstorm. So anyways, that's logarithms are involved in that thing there. So it's very practical stuff. So there's two special logarithms. The common logarithm is the base 10, and the natural logarithm is base e. Come on, you just did that. I don't know why I didn't want to do that. So here on the scale here, right, there's the log. Because it doesn't say the base, that's log 10, that's common logarithm. Notice it here, I didn't write the 10, you just say log x. And then underneath that is ln, that's natural logarithm, and that's log base e. Now, in the real world of math and science, the natural logarithm is the one you're almost always using. You don't, usually if you say just log x, everybody knows you're talking about ln. You're not talking about log base 10. There's a few applications of log base 10, like the Richter scale for earthquakes. Right? They don't tell you the actual value of the strength of the earthquake. What they're telling you is the exponent raised to a power of 10. So like if you go from a Richter scale reading of 6 to 7, that's 10 times stronger. It's not 1 stronger, it's 10 times stronger. So, but most of the time when you say logarithm, you really mean ln. So you shouldn't be confused by that. Ln is right there. Now there's a fair amount in the text of just like, okay, let's use the calculator and let's find log of 2. Let's find log of 10, I'm not going to go through all that stuff. It's kind of simple stuff. You got your calculator, you know where the buttons are, boom, boom. You don't need to set modes or anything like that. Not like trigonometry. Okay. So here's properties of logarithms. And they've got it in there. I don't know if it used to have this stuff in here. I used to always add it myself, but now it's in there. So here's one property. The log of 1 equals 0. It doesn't matter what the base is. The log of 1 equals 0. Now, if I converted that to an exponential, again, a to the 0 equals 1. That's this right here. Well, we know by properties of exponents, anything to the 0 equals 1. That's why the log of 1 equals 0. The log of a, log base a of a equals 1. So basically, if you're taking the log of something, which is actually the base of the logarithm, it's like they cancel each other out. Again, if you convert it, a to the 1 equals a. It's just like saying anything to the first power equals itself. Even more useful is you could say a log base a of a to the x equals x. So it's actually more specific. It's telling you it doesn't have to be an exponent of 1 here. Whatever is that exponent here, that's going to be the answer, as long as these two match up. And we use that all the time when we're solving equations. right? We try to match up the base of the logarithm with the base of the exponential that we're trying to simplify. You can see a to the x equals a to the x. Okay, and let's see, log base a of x equals log base a of y, then x equals y. So two logarithms of the same base, they can't be equal to each other unless the arguments are equal to each other. So x must equal y. So we should be able to use those properties to simplify logarithms, like the first one, the log base 4 of 1. Which property do you think we're going to use? The first one, right? The log of 1 of any base equals 0. Right, that's because of number 1. I can't even put it there. B, simplify. Log base square root of 7 of the square root of 7 should equal, by this property here, since the base matches the argument, 1. So this is by the second rule, equals 1. Okay. 6 to the log base 6 of 20. What do you think? Doesn't that look like this one? So a to the log base a of x equals x. So 6 to the log base 6 of 20 equals 20. And that is by the third rule. Okay. So try to do these three. Use the same properties, see if you could simplify. With the first one. Right? Since the base matches the argument, 1. Second one. Since the base of the exponential equals the base of the logarithm, that's like this one. The answer is 3. What about this one?
1.
So log base 3 of 1, which one of those three properties you can use? The first one, which says the log of 1 is always 0. I want to go back to the definition again. So notice here that they said that the a has to be greater than 0. Well, since we're going in between exponentials and logarithms, we already said for the exponentials that a was always greater than 0. So even when you got a base of a logarithm, it's always going to be greater than 0. But notice in our examples here that you can have like irrational numbers be the base of a logarithm. So there's nothing against that. You can have anything but just not negative, not 0. So find the inverse. So remember the steps we use to find the inverse of a function. First, if it's in function format like that, function notation, we substitute y, right? So that would be the first step. Y equals log base 2 of x. Second step, we would say solve for y. Okay. Well, how do you solve for y? When in fact then you switch the x and the y. Sorry. X equals log base 2 of y. Now you have to solve for the y. How do you solve for the y when it's like inside the log function? Remember, this is called a transcendental function. It's not the kind you can just do algebra to both sides and eventually isolate the y. What were you going to say, Michael? You convert it to an exponential, right? Remember, as an exponential, it's going to be 2 to the x equals y. So what you notice is logarithms and exponentials are inverses of each other. They undo each other. Just like squaring undoes a square root. Logarithms undo exponentials, exponentials undo logarithms. So when we get to the point of having to solve equations, if we have an exponential equation, we'll take the logarithm of both sides. If we have a logarithmic equation, it's called exponentiate. We'll exponentiate both sides. Or we'll convert it to an exponential. We'll see when we get to that point. That's not a today thing anyways. But so I'm going to call this now f of x 2 to the x. So logarithmic and exponential functions of the same base are inverses of each other. Okay, here's your 2 to the x. Here's your, log base 2 of x. This is 2 to the x. So remember the things that we're supposed to understand about inverses. The graph of a function and its inverse should look like they're reflections across the line y equals x. That's this line right here. And they do. This looks like it's the mirror image of this one. This is the line of symmetry that goes in between them. The points on the exponential, if I find a point on the exponential, like this one, the exponential had a y-intercept of 0, 1, the logarithm must have a point 1, 0. That's why the log of 1 equals 0, no matter what. Right, so this is 0, 1. This is 1, 0. Okay, where the, let me see if I've got this done. That's good. The exponential had a asymptote here, then the logarithm must have an asymptote here. So the graph of the logarithm is approaching the line x equals 0 as an asymptote. It gets infinitely close, but it never touches, right? It can never have a value of 0, and it certainly can't be negative. So all those things follow from the fact that these two are inverses of each other. So here's I'm not so interested in all the transformation stuff, a little bit. We should know that stuff cold by now. But this kind of stuff is kind of important. Being able to look at a logarithm function and understand, for example, that the domain is from 0 to infinity. Right? It's not all real numbers because it can't get to the left of the y-axis. It can't even touch the y-axis. Okay? The range, this may not look like that it goes on forever, but it does. Just like an exponential had a domain of all real numbers, then this must have a range of all real numbers. The x-intercept has to be 1, 0. It's always increasing. They say it's 1 to 1, therefore it has an inverse function. We did use that term when we were doing inverses before. Does a function have an inverse? If it's 1 to 1, it does. What was the test that we used to determine whether a function had an inverse?
Horizontal line test.
A horizontal line test. Does it look like this would pass a horizontal line test? Yeah, it does. So it should have an inverse. Obviously it does. It's exponential. It has a y-axis as a vertical asymptote. It's continuous. There's no breaks in it at all. And it's a reflection of the exponential. So the important thing, and again, if you go on to calculus next year, you'll deal with this function quite a bit. And you need to understand that this is the third example of a restriction to domain. We already knew that you can't divide by 0. That would introduce a restriction to domain. You can't take the square root of a negative number, right? And now we can say you can't take a logarithm of 0 or negative numbers. Those are the 3 restrictions to domain that we know so far. So transformations of logarithmic functions are the same as all the other functions that we've dealt with. This one here, the log of x, is the parent function. If I subtract 1 inside the function, that should be a shift to the right. So notice that the parent function had the point 1, 0, so the transform function has the point 2, 0. I went to the right one. Where's the asymptote on this one here? If it was shifted to the right one, now where's it? Okay, now the asymptote should be at 1. Let's see that. What's the domain? 1 to infinity? Close. I mean, if you're saying that the domain is x is greater than or equal to 1, that's incorrect. What is it?
Greater than 1.
It's just greater than 1. So 1 to infinity, but you got to make sure you say it's not inclusive. So it does not actually get to 1. It gets infinitely close, but it doesn't get there. Okay, so let's see, this one is plus, they put it in front, which they'll do sometimes like that to make it clear that if they would have written plus 2 after with no parentheses around the x, then you might think, oh, well, is that like plus 2 inside, or is it supposed to be plus 2 outside the function? When they put it in front, it's clear. Okay, this is like outside of the function. What does it do normally when you add a number after the function? It goes up. So this function, you know, this is the parent function, this is the transform function. Does that move the asymptote to go up and down? No, this vertical line would stay in the same place. So it doesn't change the domain, range, anything. Now, most of you, I think that if you got a calculator from us, you know, you got an 83, probably. Calculator doesn't do a good job of doing logarithms. If you put a logarithm in the calculator, even I can do it here. Okay. I'm going to do just scoot it away a little bit. I'm going to go log of x minus 3 plus 2. X minus 3 plus 2. And I'll do a normal zoom 6. So there's 2 things that are wrong about that, right? This graph goes on forever. There's an asymptote at 3, and the graph is getting infinitely close, but it never touches. It certainly does not stop there. So that's wrong. You have to know better than your calculator. Don't let the calculator fool you on that. The other thing is that it almost looks like there's an asymptote here, like it's not going to go above a certain value. That's not true. There's no asymptote horizontally. It'll go all real numbers for range, no matter what. No matter that it looks like it's flattening out, it's not flattening out. It's just going up really, really, really slow. So don't let the calculator fool you about this. Okay, so use the graph of f of x equals log base 3 of x, that's this right here, to sketch the graph of each function. So it says you try, but I'll just go along with you here because it's hard to draw these things. But this is actually a screen capture from Desmos, which is not a bad graph, really. Easy to see, certainly better than that, you know. And see, it did not cut it off. Okay, so let's see, what's the transformation on this one here? The parent function is just the log base 3 of x. What's this minus 1 doing to the graph?
Down 1.
Down 1. So, I mean, I only know, I can say I only know 1 point, okay, which is that point right there. So I know that one goes down 1. But is there another point on the graph of the parent function that looks like it'd be easy to move?
3, 1.
Yeah, 3, 1. But, so why do we have that point? Well, if you plug in 3 here, log base 3 of 3 by the properties should equal 1. So that's always, if you have to like come up with another point, that's always an easy one. Make the argument inside equal to the base, and then you can plot. that point right there. So we know we have that point. And then does that move the asymptote at all? No. So, I mean, with just those points and knowing that there's an asymptote here, I should be able to just sketch in a graph that looks pretty close. Okay, what's this transformation of a +3 inside the function? Go left 3, okay. So is that going to move the asymptote to go left 3? So I would sketch that first. Let me put in the asymptote. I think I'm good here. Right there.
Shouldn't it be at -2? Oh, no.
Not the asymptote. Remember, the asymptote was here. It has to go 3. What is it that's going to be at -2?
X-intercept.
Yeah, this had an x-intercept at 1. If I move that 3 to the left, 1, 2, 3, that's where that point is now. And again, which is the other point that would be easy to move?
3, 1.
Because that one right there. So 1, 2, 3, that would go about right there. Well, what's the x value at that point? What's the x value?
0.
It's 0, right? Okay, well look what happens. If I plug in a 0 here, then I've got log base 3 of 3 equals 1. So I can sketch that in. Something like that. What is the domain?
X is greater than -3.
Right, the domain is -3 to infinity. What is the range?
All real numbers.
All real numbers. Logarithms are always ranges, all real numbers. So the natural logarithm is just an example of logarithms. I mean, the logarithm definition we got before was log base a, where a could be anything. So I mean, this is just like one example. Okay, a is e. But you can definitely then show it as ln of x, the natural logarithm. And that makes all those properties, right, just change how they look a little bit. Now we say ln of 1 equals 0. Right? Ln of e equals 1, because the base of the log, if it's ln, is e. E, so it's 1. Or e, x. So these are the same properties. We don't really need another definition of them, in my opinion, just because, you know, the other one was the log base a, and they could be anything.
Teachers, excuse this interruption. At this time, we need all 10th grade classes, teachers, and students to report to the auditorium. Thank you.
So again, using those same properties, then we should be able to simplify these expressions. Now, here's where it's starting to get a little more tricky, not because it's ln, just because they're throwing in a little more complicated. For example, ln of 1 over e, what do you think that's going to be? Do we have anything up here that talks about ln of 1 over something? Nothing like that at all, right? So how could I change this so there's actually 1 over e is written as e to some power? E to the -1, right? So you would write this as ln of e to the -1, and then which property would apply? This one. Ln of e to the x equals x. So what does this one equal? -1. Since the base of the logarithm equals the base of the exponential that's inside, then it's just the exponent comes out. How about this one? E to the ln of 5. Which property is that? It's this right here. E to the ln of x equals x. So in this case, it equals 5. Okay. ln of 1 all over 3. Which property applies? Just look at the numerator. What property applies? ln of 1 equals 0, right? Log any base of 1 equals 0. So this is 0 divided by 3, which is 0. Hopefully the divide by 3 part isn't causing problems. How about 2 ln of e? What's ln of e? What is ln of e? 1. So this is 2 times 1. 2. Or what you could do is, well, I guess I can't do that yet. So it's 2. Later on, we get there's more properties of logarithms that we could have changed that. So try this one. This is your you try. Try to do those 4. So what'd you say in the first one? 1/3, right? That's this property here. ln of e to the x equals x. So ln of e to the 1/3 equals 1/3. How about 5 ln of 1? 0, because ln of 1 is 0. So that's 5 times 0, which is 0. How about 3/4 of ln of e? Okay, what's ln of e? 1. So this is 3/4 times 1, which is 3/4. How about the last one? E to the ln of 7 equals 7. Sorry, 3 sides left. So find the domain of each function. So what would be the domain of the untransformed parent function? What did we say? What's the domain of the? Say again? X is greater than 0, which in the interval notation we write like 0 to infinity, right? Okay, well, what kind of a shift is this? The first one, -2. -2 inside means right 2. Okay, so this is right 2. So what's the domain? 2. Now it's 2 to infinity. Okay. Okay, what's going on in this one here? I mean, it looks like there's a 2, right? Definitely it's either going right or left. It's a little confusing because now there's a minus in front of the x. And what does the minus in front of the x usually do? It flips it across the y-axis. Now personally, I get confused looking at these, but it's useful just to put in some points. Like, what is it that I would plug in for x that would make this thing equal 0? The argument equals 0. 2, right? So definitely, if I looked at the graph, it's going to have the asymptote now is going to be at 2. Okay, now the only question means that it's going to approach either on this side or on this side. We just have to figure out which one. So which one is it? If I put in a value of x, which is to the right of the asymptote, 2 minus 3, would that work? No, then I'd be taking a log of a negative number. So this thing has actually been moved 2 to the right, and it's been flipped to go to the other side. That's not very accurate because actually we know that it had an intercept right there. But what is the domain?
Negative infinity to 2.
Good. So it starts at negative infinity and it ends at 2, not inclusive. And how about the last one? Is it being shifted up, down, left, or right? The answer is no. It's not being shifted. So on the parent function was 0 to infinity, right? We could not have values that were 0 or negative. But what's going to happen if you put a negative number into x squared? It becomes positive. So actually you can put negative numbers into this. Can you put 0 into it? No, you still couldn't put 0 in, but you could put negative numbers. So what's the new domain? X does not equal 0. It could be anything else. So what is the domain of that? I think we already did this. What kind of shift is that? Left 3. So what's the domain? So the domain would be x is greater than negative 3. Negative 3 to infinity. So here's our word problem. Students participating in a psych experiment attended several lectures on a subject and took an exam. Every month for a year after the exam, the students took a retest to see how much of the material they remembered. The average scores for the group are given by the human memory model. So f of t, which is months, is 75 minus 6 times ln to the t plus 1. So what is this 0 less than or equal to t less than or equal to 12 represent? Alex? You know, it's not necessarily a restriction, it's a domain statement. So whenever you have like comma and then it's giving, that's just telling you can only plug in values from 0 to 12. Not because they would make it undefined, but just saying that the model doesn't work outside of 0 to 12 months. Okay. So what was the average score of the original exam at t equals 0? What are they asking you to do with that t equals 0? Just plug it in, right? Plug it in. So for A, we're going to get f of 0 equals 75 minus 6 times ln of 0 plus 1. Okay, but that's 75 minus 6 ln of 1. Well, what's ln of 1 equal? 0. So this is just 75. So that's 75, the constant term in front, that was the original score. Okay, B. What was the average score at the end of 2 months? What are we going to do with the 2?
Plug it in.
Plug it in, right? F of 2 equals 75 minus 6 times ln of 2 plus 1, which is 75 minus 6 ln of 3. And we would have to put that in the calculator. Not there. Second. So 75 minus 6 ln of 3. And I'll use the parentheses, that's good. 68.4. And then last, at 6 months. Right. 6 months, you're going to plug in 6. So we're going to get 75 minus 6 ln of 7. So, second, enter, 7, enter. 63.3. So it dropped. It was 75 and now it's gone down to 63. So the way they presented in this problem, it sounds like this is a real thing. You know, that there is such a thing called a human memory model. Somebody probably just collected a lot of data and then they did a regression line to get the best match that they could. And that's what it is. So that's it. And that's the homework.